Hi, welcome to this lesson on Euclidean geometry, similarity and congruency. Let's have a look at question 6. ABCD is a parallelogram, so that's important, with diagonals intersecting at the point F. FE is drawn parallel to CD, so in the diagram we can see that. Then AC, in one of the diagonals of that parallelogram, is then produced outwards to reach a point P here, such that PC is twice the length of AC. So if I let this length AC equal x over here, this diagonal length AC, right, that total length there, x, then PC, this length here, is twice the amount of x. Then AD is produced, so this side of the parallelogram, to the point Q such that DQ is twice AD. So if I let this side length of the parallelogram be y, then DQ is 2 amounts of y. Alright, and that looks pretty interesting because if you look, there's a parallel line CD, but we don't know that PQ is parallel because that wasn't given to us, but we're given the sides are in proportion. So we can automatically conclude that that line is parallel. So that might be a question that gets asked. Alright, so the first question they are interested in asking is show that E, this point here, is the midpoint of AD. So I'm going to construct this parallelogram outside here so we can see it. So A, B, C, D. And we have the diagonals of a parallelogram. So because this is a parallelogram, there's a lot of information we can put on. So for example, these two sides BC and CD are parallel. We're also given the point E here is also parallel from F. We also know that BC is parallel to AD. That's another point of parallelograms. But what other information of a parallelogram do we know that we can use? Well, we know the length AB is equal to CE and the length BC is equal to AD, right? But we also know that diagonals bisect each other. So therefore, I can say that this length here, AF, is equal to FC. Okay, that's going to be really important because that means that F is a midpoint of the line AC. So look at this. You've got a midpoint on the line AC that is going parallel to the third side CD in this triangle ACD. So if I draw this triangle ACD, you've got a midpoint F that is traveling parallel to a third side CD to this point E here. So by the converse of the midpoint theorem, this means that this side AE must equal ED. But that's exactly what we wanted to show here. So if I want to put this into the proof format, a rigorous proof here, how do I do that? So I can first of all say that the line AF equals the line FC, and that is because ABCD is a parallelogram, so you can write PARM for short, P-A-R-M. So therefore, diagonals bisect. All right. Then you also know that line FE is parallel to line CD that was given. So therefore, you can say that E is the midpoint of AD, and the reasoning for that is the converse of the midpoint theorem. Okay, so the midpoint theorem, remember, just says that if you have two midpoints on two sides of triangles, and you draw a line between them, then that side is parallel to the third side. But we were given the converse information. We were given one midpoint, right? F, the midpoint of line AC, that is traveling parallel to a third side CD to the opposite side of AC, which is AD. So therefore, by the converse of the midpoint theorem, E must be the midpoint of AD. All right, so that's how we would prove this first question here. Next, they want us to prove that PQ, this line here, is parallel to FE. Okay, so like I said earlier, it is interesting that we were given those proportions. Okay, so if I draw this larger triangle out here, all right, AQP here, then I have a line CD that is going parallel to another line FE here. All right, but we were also given that this length AD, right, if we called it y, then the length of dq was 2 amounts of y. We were also given that the line AC, if I called that x, then the line PC was 2 amounts of x. So I can show my proof that they are parallel by using the converse of the proportionality theorem now. So recall, the converse of the proportionality theorem says that if you have two sides of a triangle, right, where a third side is drawn that cuts that triangle into equal proportions, then that side must be parallel to the third side, in this case PQ. So what we have here is that if I look at this proportion here, AD divided by DQ, that's going to give me y over 2y, which is equal to a half. And then if I look at this proportion here, AC over CP or PC, that's going to give me x over 2x, which is equal to a half. So therefore, I show that AD over DQ is equal to AC over CP. Okay, so I've shown that proportionality is true and that there's a line from C to D that is drawn, right, opposite the side PQ. So therefore, I can say that PQ is parallel to CD, and that is by the converse of proportionality theorem. Okay, but I've not proven that PQ is parallel to FE. I've proven that PQ is parallel to CD. And we know that CD is parallel to FE. That was given to us as the information. Okay, so therefore, if PQ is parallel to CD and CD is parallel to FE, then by the transitive property of parallelness, which just means that PQ must be parallel to FE as well. All right, and that is how we would prove this type of question. Lastly, they tell us if this length PQ is 60 centimeters long, calculate the length of FE. Okay, so how are we going to do that? Well, we can use some sort of proportionality to work with sides. So we need two triangles that are similar to each other. Have we proven any two triangles that are similar? Not yet. Okay, so we need to look for triangles that are going to be similar to each other, and then we can use the proportionality of the sides. Okay, so I'm going to look at these two triangles here, APQ. I'm going to look at the smaller triangle inside of it, ACD. I'm going to claim that these two triangles are similar. Well, certainly, I know that angle A is equal to itself. They are common angles, so they must be equal. But I also know that CD is parallel to PQ. We've just proven that, right? So therefore, by corresponding angles, this angle here must be equal to that angle here, right? The F shape there. Okay, there's the corresponding angles. And furthermore, if I have those two angles equal to each other, therefore by sum of angles in triangle, this angle Q must equal that angle D. Okay, so I'm going to start off with my proof by claiming that triangle APQ is similar to triangle ACD by angle, 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 and I've given my logical approach here in the diagrams. Okay, so you can use that logical approach, write out the steps there. Then, from this proportionality, I need to look for side lengths that I've been given. I've been given PQ is 60 centimeters, so I'm going to want to use that one. All right, and then I need to find other side lengths that I can work with. So we were given some proportionalities earlier here, recall. This was y, and then this was 2 amounts of y. This was x, and therefore this was 2 amounts of x. So that might be useful, okay? But let's just go ahead and check. So I'm going to use PQ in this larger triangle, and let's use AP, all right? AP, which is this one here. So this larger side. So the larger side is made up of this little x plus this 2x, so it's 3x in proportion here. And then similarly AQ, that's y plus 2y is 3y. Okay, this was 60 centimeters given. Then AC was x units and AD was y units. And the goal, remember, is we're looking for the length of FE. Okay, so just keep that in mind. Okay. Next, I'm going to show that CD, this length here, is exactly twice the amount of FE. Okay, so if I bring out this other smaller triangle here, so ACD again, but then this time the line FE, we've proven that these were midpoints. Okay, so by the midpoint theorem, not only are these lines parallel, which we already given, we know that this length FE is half the length of CD. So I can say that CD is twice the length of FE, and that is by the midpoint theorem. Because whenever you're given anything with midpoints and midpoint theorem, it's always good to use all that information about it. All right, so that means if I can find the length CD, I just need to multiply, or rather divide by 2 to get the length of FE by itself. Okay, so that's the goal. We're looking for the length of FE. Okay, so I can say therefore FE equals a half times the length of CD. So I'm interested in this length CD here. Okay, so I'm going to do PQ over AQ, and I'm going to do CD over AD for this proportionality. So now I'm going to say that PQ divided by, PQ divided by CD. No, okay, so let's just correct that quickly. All right, so I'm going to go PQ over AQ. That's going to be equal to CD over AD. Okay, so I know PQ is 60 centimeters, that was given. The length of AQ, I don't have the exact length, but I know it's written as 3y in my current diagram. CD is, we don't know that. That's a length we're actually looking for, so we can plug it back into this equation. And then AD, right? And AD, where's AD? That's this length here, y. Okay, so let's move around these objects here. So PQ, so I want CD by itself, so I'm going to multiply both sides by AD. So it's going to be PQ over AQ times AD equals CD. All right, so CD equals, what is PQ? PQ is 60 centimeters. Okay, AD was given as y divided by AQ. AQ was 3y. Okay, so the y's will divide, and 60 divided by 3 is 20. So CD is 20 centimeters. So if I come back to here, therefore FE must be a half of 20, which is 10 centimeters. Okay, so that is the logical progression of finding the length FE. Again, it has to use similar triangles somewhere to get sides in proportion to each other, and then isolating which side do you actually want to work out. In this case, we needed an extra step, the midpoint theorem, to be able to work out the length of FE. All right, so that's how we would do this type of question. I'll see you in the next one.